Hello students, welcome to Turito. Today in the class we are going to start new topic modern physics, and in the modern physics the subtopic we are taking first is the Bohr atomic model. But before coming to the Bohr atomic model, we must learn about the some history of the atom, and in the NCERT book also lot of things are given on the how atom was discovered, especially on the Rutherford experiment. Lot of things were given in the NCERT book. So all the students who are preparing for IIT-JEE or NEET, they must go through all this, especially Rutherford experiment. I will not say that Thomson and Dalton's atomic model you must go through in extensively, but Rutherford's model you must study. So today almost in all the class, in the whole class I will discuss Rutherford's model and keeping the base of the NCERT book. Okay. In the beginning of 18th century, scientists started thinking about that there must be some small particle, very small unit of mass that constitute the ordinary matter. There were enough clues that were indicating that there must be a small unit of mass that constitute the ordinary matter, but actually what it looks like and what is the configuration, what is the size, what are the properties, what kind of charge is there, what kind of particles are there, it was not known. The first significant experiment done was by the Dalton. Dalton after experimenting collected some data, and on the basis of that data he proposed that there must be a small unit of the mass for ordinary material or ordinary matter, and that small unit is the atom, and the type of atom he proposed that was not satisfying many other things, many other experiments. That is why that was not accepted, but it was the first step towards the discovery of atom. And in the meantime, after some years, many scientists were finding that if they consider a gas as a collection of small particles, if they consider gas a collection of small particles, then on the basis of kinetic theory of gases, various properties can be explained very effectively. If gas is considered as consist of many small particles, then kinetic theory can explain many not only chemical, physical properties also, or physical phenomenon also, like diffusion and viscosity. These things can also be explained if we assume matter or gases are collection of small particles. But after several years of the Dalton's experiment or data, nothing significant happened. But in the late 18th century, around 1897, when Thomson discovered electron, so after discovery of electron, a greater breakthrough came in the support of existence of atom, and that time after discovering the electron, Thomson also got the very good reputation in the scientific world, and he proposed a atomic model, and that was initially accepted, welcomed very well by the science world. And that model of atom he proposed was called plum pudding model. So let us check what was the highlights of Thomson's atomic model, and I am today's lecture I am taking NCERT as the base. Okay. So many things you will find I have taken directly from NCERT book to explain you, but for the JEE level and JEE advanced level things, while we will be discussing Bohr atomic model, I will consider different approach. The first model of atom was proposed by J.J. Thomson in 1898. In 1897, he discovered electron, and after discovering electron, he proposed the atomic model. In his model, he proposed that the positive charge of the atom is uniformly distributed throughout the volume of the atom. He assumed positive charge is distributed throughout the volume of the atom, and negatively charged electrons are embedded in it like seeds in watermelon. Okay. However, subsequent studies on atoms as described in this chapter showed that the distribution of electrons and positive charges are very different from that proposed in this model, because this model was not satisfying atomic spectrum. The lines in a atomic spectrum could not be explained on the basis of this atomic model. That is why it was not accepted. Then came the Rutherford's atomic model, and this model was a great success. It is not a failed atom. By the experiment of Rutherford, we got idea of the atom which still we accept. The atom is of this kind. Basically, Rutherford proposed atom after doing an experiment. So, an experiment was done by the Rutherford, and on the basis of result he got on that experiment, he proposed an atomic model. So, let us first move to the final Rutherford's model step by step. Rutherford, a former research student of J.J. Thomson, was engaged in experiments on alpha particles emitted by some radioactive elements. So, basically Rutherford was experimenting with the radioactivity of the material. In radioactivity, the material which are radioactive emits alpha particles, sometimes they emit beta particles. Alpha particle is a helium nucleus which has 2 protons, 2 neutrons. At that time it was not known, but now we know that it has 2 protons, 2 neutrons, and positive charge is equal to charge of 2 protons. Okay. In 1906, he proposed a classic experiment of scattering of these alpha particles by atoms to investigate the atomic structure. This experiment was later performed around 1911 by 2 of his students, and one of the student was just 20-year-old. Okay. The explanation of the results led to birth of Rutherford's planetary model of atom. Thomson's model was given the name plum pudding model. Rutherford's model was given the name planetary model. Okay. According to this, the entire positive charge, this is the important thing, the entire positive charge and most of the mass of the atom is concentrated in a small volume. This small volume is called the nucleus, with electrons revolving around the nucleus just as planets revolve around the sun. That is why it is called planetary model. Rutherford's nuclear model was a major step towards how we see the atom today. Okay, so the Rutherford's model, in various books it is written that Rutherford's model was failure and Bohr atomic model was the successful. No, the Rutherford's atomic model was a great success. Only one thing it could not explain, or Rutherford could not explain. The model was correct, but in that model one thing was not explained by the Rutherford: how electrons revolving around the nucleus and without losing energy. If electrons are losing their energy while revolving around the nucleus, after some time these electrons will finally fall in the nucleus and the whole atom will collapse. It could not be explained by the Rutherford. So, Rutherford's nuclear model was a major step towards how we see the atom today. However, it could not explain why atoms emit light of only discrete wavelengths. How could an atom as simple as hydrogen, consisting of a single electron and a single proton, emits a complex spectrum of specific wavelengths? The classical picture of an atom: the electron revolves around the nucleus much like the way planet revolves around the sun. However, we shall see that there are some serious difficulties in accepting such a model. The configuration, the construction or the structure of atom, which is defined on the basis of this model, Rutherford's model, still we accept today. The things which this model could not explain, it is a different issue, but structure of atom we still accept, which was proposed by the Rutherford's atomic model. Before moving forward, let me explain one thing. Atomic spectrum. Actually, this Rutherford's model was unable to explain the atomic spectrum. So, what is the atomic spectrum? Suppose this is a container, and suppose this container has hydrogen gas. Okay, and white light is sent on this container. This is a transparent container, and white light by white light we mean that all the wavelengths are allowed to fall on this hydrogen gas. So, all the wavelengths, radiations of all the wavelengths are passing through the hydrogen gas, and when these rays comes out of the container after passing through the hydrogen gas, it is observed that some wavelengths are missing. Some wavelengths are missing in this spectrum. It means that those wavelengths have been absorbed by the hydrogen. So, this spectrum we get after absorption of some wavelengths, that is why it is called absorption spectrum. And after, when white light is passed through the hydrogen gas, there is another spectrum is observed, and that spectrum is emitted by the hydrogen gas atoms. So, here we get some other spectrum, some other wavelengths. This is called emission spectrum. Emission spectrum, and in this spectrum missing wavelengths missing, those were missing in this absorption spectrum are present, and some other wavelengths are also present. Other than missing wavelengths, some other wavelengths are also present in the emission spectrum. So, two type of spectra are defined, one is emission spectrum and other is the absorption spectrum. When white light is passed, hydrogen gas absorbs some of the wavelengths, so some wavelengths are missing here, but in this emission spectrum certain wavelengths are present. These are called some spectral lines also. When carefully observed by strong or efficient or the spectrometer of high resolution, it was observed that in this spectrum certain lines are present, lines having some certain wavelengths. So, this question could not be answered on the basis of Rutherford's atomic model, that hydrogen atom has only one proton and one electron. Then why emission spectrum has so many wavelengths? It must have only single wavelengths. Why so many wavelengths are present in the emission spectrum? This could be explained. This could be explained after proposition of Bohr's atomic model. Okay, but structure of atom Bohr also accepted as it is, that was proposed by the Rutherford or Rutherford's alpha particle scattering. Now, we focus on this famous alpha particle scattering and Rutherford's nuclear model of the atom. So, this is the setup of a rough view of the alpha particle scattering setup of the Rutherford's experiment. So, here this is a container. In this container, actually it was not container there, something a different kind of arrangement was there in actual experiment. So, here consider there is a container. In this container a radioactive material is put, and that radioactive material is radiating or emitting, that radioactive material is emitting alpha particles. Alpha particle means helium nucleus. These helium nucleus comes out of the small opening in this container, and this helium nucleus are focused or collimated through this small opening of the screen on this gold foil. This is a rectangular gold foil. Its thickness is very less, it is very thin. Okay. A beam of 5.5 mega electron volt alpha particles. So, these alpha particles were carrying kinetic energy of 5.5 mega electron volt. Alpha particles emitted from a bismuth radioactive source at a thin metal foil made of gold. This is a thin metal foil made of a gold. Okay, thickness is very small. Alpha particles emitted by this radioactive source were collimated into a narrow beam by their passage through lead bricks. So, lead bricks were put. This is another diagram I will show you later. The beam was allowed to fall on a thin foil of gold of thickness 2.1 into 10 to the power minus 7 meter. So, some data you must also remember. Thickness of gold foil is around 2.1 into 10 to the power minus 7 meter. The scattered alpha particles were observed through a rotatable detector. This is a screen and a detector is placed here. Suppose detector means this is a spectroscope. This spectroscope can move at 360-degree angle. If this is the circular screen, then a spectrometer can rotate like this. Actually, after hitting the gold foil and getting scattered, these alpha particles hits this screen. This screen is made up of a certain material. So that what happens when a alpha particle hits the screen, a flash of light appears there, and that flash of light can be observed with the help of a spectrometer, and even we can count how many flash of lights are there. So, how many alpha particles actually hitting the screen we can calculate. So, the scattered alpha particles were observed through a rotatable detector consisting of zinc sulfide screen. Screen is coated with zinc sulfide. Zinc sulfide screen and a microscope. The scattered alpha particle on the striking the screen produced brief light flashes or scintillations. These flashes may be viewed through a microscope, and the distribution of the number of scattered particles may be studied as a function of angle of scattering. Okay. This section I have taken directly from NCERT book. So, it will be helpful for you for your 12th class also. And if you are preparing seriously for JEE, solve each question of NCERT also. So, particles may be studied as a function of, and this is the setup, this is the screen. Okay, now we move another diagram. So, schematic arrangement of the experiment. This is the source of alpha particle. These are lead bricks with a small opening between them. Through this small opening, alpha particles can pass in the form of a narrow beam, and these alpha particles hits this screen or gold foil, not screen, this is a gold foil, and this is the zinc sulfide screen. When a alpha particle hit the gold foil, after collision it can move in this direction, and when this alpha particle hits the screen at this position, a scintillation is produced or a brief flash of light will be produced, and that flash of light can be observed by this detector. Detector means microscope. And by counting the scintillations, how many scintillations are per second hitting, we can also found that how many particles are hitting at a particular angle per second. This we can calculate. And gold foil target about 10 to the power minus 8 meter thick, some are deviated through a large angle theta. This angle theta is called angle of scattering or a scattering angle. Okay, this is the setup. Now move ahead. This is also another important thing. A graph is plotted between number of scattered alpha particle and on the x-axis angle of scattering. Angle of scattering. So, 0 angle, 20 degree, 40 degree, 60, 80, 100, 120, 140, 160 and 180 degree. So, on the x-axis we have taken angle of scattering, and on the y-axis we have taken number of alpha particles which have scattered at particular angle. Okay. Here these dots, the dots in this figure represents the data points. These dots are the actually data which collected after the experiment, and these various dots were joined by a smooth curve, by a line, and we get a smooth curve. So, basically data points are the dots, and after joining the data points we get roughly a line which looks like this, which we are looking at the diagram. So, dots in this figure represent the data. Many of alpha particles pass through the foil. It means that they do not suffer any collisions. Only about 0.14% of the incident alpha particles scatter by more than 1 degree. If you look at the data available in this diagram or in the graph, you will see that this number is huge, corresponding to a small scattering angle. If you suppose this will be corresponding to 1 degree or 2 degree. So, a huge number is scattered at 1 degree, and almost or several particles which are not scattered at all. There are a great number of particles, a big number of particles which do not scattered at all. And this is the data also. 0.14% of the incident alpha particles scatter by more than 1 degree, and this is very important thing, and about 1 in 8,000 deflected by more than 90 degree. So, more than 90 degree, if you want to check how many particles are deflected at 90 degree or more than 90 degree, you see that this line is very height of these points is very less from the x-axis. So, this number is very less as compared to this number is very less. Okay. So, there are very few number of particles, that is 1 in 8,000, which is scattered at angle more than 90 degree. Rutherford argued that to deflect alpha particle backwards, but there is rarely a particle is also found which is scattered at angle 180 degree, and this was the catch which Rutherford explained. That Rutherford argued that to deflect an alpha particle backwards, it must experience a large repulsive force. If a particle retraces its path due to repulsive force, then repulsive force must be very strong. If repulsive force is very strong, then that repulsive force must come from the positive charge, because alpha particle itself is carrying positive charge, and positive charge inside the atom must be concentrated at a point, so that that whole positive charge which is concentrated at a small volume can give a significant repulsive force to the alpha particle. And one more important thing is that scattering or deviation is more if mass of two particles is comparable, that is, as the difference in mass is bigger, deflection is lesser or deflection is smaller. If two particles of same mass collide, then chances of deviation and deviation or deflecting at greater angle are more. If suppose a particle of 1 gram collides with a particle of suppose 1000 kg, then it will not deflect it much. Okay? But if two particles of same mass are colliding, then there are greater chances of transfer of momentum and energy. So, Rutherford argued that to deflect the alpha particle backwards, it must experience a large repulsive force. This force, the argument continues now still. We have moved on the next page, but argument of the Rutherford is continues. This force could atoms be provided if the greater part of the mass of the atom and its positive charge, two things, mass of the atom and positive charge, were concentrated tightly at the center. The mass also be concentrated at the center, because only in that case mass of the atom will be comparable with the mass of the alpha particle. And to give the strong repulsive force, the positive charge also must be concentrated at the center in a small volume. This was the argument. Then the incoming alpha particle could get very close to the positive charge without penetrating it, and such a close encounter would result in large deflection. So, to get large deflection, encounter must be such that mass particle collides with a particle of greater mass, and charge must also be concentrated in a small region. This agreement supported the hypothesis of the nuclear atom, and this is very important thing. This is why Rutherford is credited with the discovery of the nucleus. The discovery of electron goes to the credit of discovery of electron goes to the Thomson. Similarly, Rutherford is credited with the discovery of nucleus. Now, move quickly to some other points. In Rutherford's nuclear model of the atom, the entire positive charge and most of the mass of the atom are concentrated in the nucleus with the electrons some distance away. Now, he is talking about electrons. So, electrons are at some distance away. The electrons would be moving in orbits about the nucleus just as planets do around the sun. The electrons would be moving in orbits about the nucleus just as the planets do around the sun. That is why it is called planetary motion. The next point is Rutherford's experiment suggested the size of nucleus to be around 10 to the power minus 15 meter to 10 to the power minus 14 meter, and it was very close to the exact value. From kinetic theory, the size of the atom was known. Kinetic theory of gases, size of the atom was already known, and it was of the value 10 to the power minus 10 meter. So, now you can think that nucleus, size of the nucleus is 10 to the power minus 15 meter, and size of the atom is 10 to the power minus 10 meter. So, atom is around 10,000 to 1 lakh times bigger as compared to size of the nucleus. Okay. So, from kinetic theory, the size of an atom was known to be this about 10,000 to 1 lakh times larger than the size of the nucleus. This is it looks very surprising, but it is true. Size of the atom is 10,000 times to 1 lakh times greater than the size of the nucleus. Thus, the electrons would seem to be at a distance from the nucleus of about 10,000 to 1 lakh times the size of the. most of atom is empty space. The final conclusion of all these points is most of the space of the atom is empty space. That is why most of the alpha particles pass through the gold foil without deviation, because they are passing through the empty space of the atom and there is no collision. With the atom being largely empty space, it is easy to see why most of alpha particles go right through the thin metal foil. However, when alpha particle happens to come near a nucleus, the intense electric field there scatters it through a large angle. The atomic electrons, being so light, do not appreciably affected by the alpha particles, because difference in mass between alpha particle and electrons is too large. So, mass difference is too great. Therefore, if two particles having great difference in mass collides, then it will not result in a greater angle of scattering. Okay. Now, consider alpha particle trajectory, and I will show you a diagram where alpha particle following a trajectory. Okay. But remember, while tracing or making alpha particle trajectory, we consider these important points or these assumptions. As the gold foil is very thin, it can be assumed that alpha particles will suffer not more than one scattering during their passage. Gold foil, after hammering, was made so thin that alpha particle will strike with only one atom of the gold. Okay. So, there is only one collision we will consider while making its trajectory. Therefore, computation of trajectory of an alpha particle scattered by a single nucleus is enough. Second point is, alpha particles are nuclei of helium atoms and therefore carry 2 units of positive charge, whereas the charge of the gold nucleus is Ze and Z has a value of 79. So, gold nucleus is much heavier and has greater charge as compared to the alpha particle. So, what happens? Gold is about 50 times heavier than the alpha particle. It is reasonable to assume that it remains stationary throughout the scattering process. Okay. So, we assume that gold atom remains stationary throughout the scattering process, and these are the trajectories. One important thing that you remember for the point of view of examination is trajectory of alpha particles in the Coulomb field of a target nucleus. The important thing is the impact parameter B and scattering angle theta are also depicted. This scattering angle theta depends on impact parameter. And what the impact parameter is? Impact parameter you already studied in class 11 in the chapter of collision. But let me tell you what is the impact parameter is. The impact parameter is the perpendicular distance of the initial velocity vector of the alpha particles from the center of the nucleus. Suppose this is the nucleus and this is the center of nucleus. Then if this is the direction of velocity of alpha particle, then and this is the center, then this perpendicular distance is called impact parameter. Therefore, for the alpha particle which is moving directly towards the center of nucleus, for that particle impact parameter is 0. For the particle alpha particle which is moving in such a way that it is just passing through the boundary of the nucleus, for this particle impact parameter is equal to radius of the nucleus. Okay. So, impact parameter means center of nucleus and direction of velocity of the alpha particle, then this distance is called impact parameter. Greater is the impact parameter, smaller is the scattering angle. Okay. If theta is small, impact parameter is less, scattering is more. I think I have spoken something reversed. Impact parameter is less, then scattering is more, and if scattering is less, it means that impact parameter was greater. Suppose this is a alpha particle which is going without any deviation, without any scattering. For this particle, if this is the target nucleus and this is the center of the nucleus, then this is the impact parameter. This is the impact parameter. So, impact parameter is too large for this, and there is no scattering. So, final conclusion is, a given beam of alpha particle has a distribution of impact parameters. Distribution of impact parameters means, if a beam of alpha particle is moving, there are several alpha particles in that. For several alpha particles, there are several impact parameters. So, impact parameter is distributed. So, alpha particles has a distribution of impact parameters B, so that the beam is scattered in a various direction with different possibilities. It is seen that alpha particle close to the nucleus means a small impact parameter suffers large scattering. In case of head-on collision, the impact parameter is minimum, that is close to 0, and the alpha particle rebounds or returns or retraces its path, for this scattering is approximately equal to pi. And for a large impact parameters, the alpha particle goes nearly undeviated and has a small deflection. The fact that only a small fraction of number of incident particles rebounds back indicates that number of alpha particles undergoing head-on collision is very small. There are very small number of alpha particles that suffers head-on collision with the nucleus. This in turn implies that mass of the atom is concentrated in a small volume. Rutherford scattering therefore is a powerful way to determine an upper limit of the size of the nucleus. Okay. With this experiment, scientists can also able to calculate radius or the size of the nucleus. Okay. So, this is the end of Rutherford's experiment. It was the topic mentioned in the class. After this, we have to study Bohr atomic model. So, what was the Bohr atomic model? Let us have some brief idea about it. Actually, there was a problem with explanation of stability of the atom, number one, and the second problem was Rutherford's model could not explain atomic spectrum. Rutherford's model could not explain number one, atomic spectrum, and number two, stability of atom, atomic spectrum and stability of atom. So, let me first talk about the stability of atom. Suppose this is the nucleus and this is the electron, and this electron is revolving around the nucleus. In physics, there is another very important field. Basically, there are two main pillars of the physics, classical physics. One is the Newtonian mechanics, you may call it, and other is the electromagnetic wave theory. The electromagnetic wave theory says that if a particle is accelerated, it will radiate electromagnetic waves. If a charged particle, to be exact, not any neutral particle, if a charged particle is accelerated, it will radiate electromagnetic waves. if charged particle is radiating electromagnetic waves, it means that it is radiating energy. And where this energy comes from? This energy comes from the energy of the particle. So, particle will be losing its kinetic energy in the process of radiating energy in the form of electromagnetic wave. So, here electron is accelerating, electron is moving in a circular path. Electron is in circular path, therefore, it has centripetal acceleration, therefore, it has centripetal acceleration. So, it will radiate energy, and if electron radiates energy, its kinetic energy will gradually decrease, and finally, after losing its entire kinetic energy, it will fall into the nucleus and the whole atom will collapse and whole atom will collapse. This thing could not be explained on the basis of, would like to say that this could not be explained by the Rutherford. His model was correct, Rutherford's model was correct, but he could not explain why electron, even being accelerated, will not lose its energy. Okay. When Bohr proposed his atomic model, he accepted construction or structure of the atom as it is, that was given by the Rutherford, but he added one point. He added that the electrons which are revolving around the nucleus, if revolves in some particular orbits, in those orbits where angular momentum of electrons, m is mass of electron, v is speed, r is the radius, then angular momentum of electron is mvr. If its angular momentum is integral multiple of h upon 2 pi, then these electrons will not lose their energy and atom will be stable. An interesting thing is that I would say it is a very funny thing, even Bohr had not known that why this will happen. Why? If angular momentum is integral multiple of h upon 2 pi, then why electron does not lose energy? Bohr not had any idea about this, but he told this, if this happens, then atom will be stable. But why this happens? Its answer could not be given by the Bohr, but answer came later and it was explained by the de Broglie. And de Broglie told that actually the classical mechanics is or the classical physics is applicable for the particles which are of greater size. But if you are looking at the particle, studying a particle which is of very small size, then only classical physics cannot explain its properties. So, we must involve quantum physics also. So, combining atom is the particle or atom is the so small is a particle where to explain its stability, classical physics and quantum physics must converge, and this thing is the classical physics. This is the angular momentum, this is the something which belongs to the classical physics, and this is something which belongs to the quantum physics. Quantum physics, that is quantum of energy, and when we talk about quantum of energy, we use a concept of photon. and energy of photon is given by h nu. Energy of a photon is given by h nu. A photon has momentum also. Momentum of the photon is given by h by lambda. Okay. So, here this is the photon which travels with the speed of light and its rest mass is 0. Rest mass of photon is 0, but still it has momentum. Momentum is a thing of classical physics. In classical physics, rest mass cannot be 0. Okay. So, a particle which has rest mass 0, but still has momentum, but that particle also has wavelength. So, this particle is enjoying both the things. It is enjoying momentum, which is the thing of classical physics, and this particle also has wavelength, which is the quantum mechanics. So, that is why this thing was explained later by de Broglie, that every particle has dual nature. Sometimes it behaves like a particle and sometimes it behaves like a wave. And later he explained that every particle in the universe also carrying a wave with it. It is called matter wave. These waves are completely different from the wave which we studied in the wave optics or the mechanical wave chapter. So, matter waves, I am not going into detail, I am just trying to tell you something about it. So, matter waves, all these things I will tell you later in detail. So, what de Broglie told? De Broglie told that every particle in the universe has wave nature also and particle nature also. So, a particle is carrying a wave with it, associated a wave with it, and this wave is called matter wave. And wavelength of matter wave is given by lambda equal to h upon mv. De Broglie told that the matter wave which is associated with a mass is given by h upon mv or h upon p, rather h upon p. It is the more appropriate expression, h by p, because in case of photon it does not has mass, but it has momentum. So, h by p is the right expression for photon also. So, lambda equals to h by p. So, these electrons which are orbiting around the nucleus also have matter wave associated with the electrons. So, if a electron is moving in a orbit, a matter wave also associated with the electron, and this matter wave has such wavelength. The wavelength of matter wave is such that in one orbit these waves completely fits. Let me explain what I am trying to say. Suppose this is the orbit of the electron, then in this orbit this is the one complete wave, this is two complete waves, three complete waves, and suppose this is four complete waves. So, these are four complete wavelengths, and after superposition of these matter waves of the same particles, they make a standing wave. It was told by the de Broglie. So, when they make a standing wave, so it becomes like this. In standing wave are represented like this. So, different loops are formed. So, electron is revolving only on those orbits where matter waves can form complete loop. Complete loop means the radius of the orbit must be such that the circumference is 2 pi r, then this circumference must be equal to either lambda or it should be equal to 2 lambda, 3 lambda, 4 lambda. That is, in the orbit, in the circumference of the orbit, exactly one wave must fit, or two wave must fit, or three wave must fit, or n wave must fit. Okay. So, what happens? This 2 pi r equals to n into, and this wavelength of matter wave is given by h upon mv. This is the circumference 2 pi r, and this is completely different from the Bohr atomic model. We are not discussing anything Bohr atomic model, we are discussing something else. So, here circumference is 2 pi r, and this circumference has such a length that it can fit either one complete wavelength or two complete wavelength or three complete waves or four complete waves or n complete waves. So, if n complete waves are fit in this circumference, then we get n into lambda equal to 2 pi r. But de Broglie also told us that wavelength of matter wave is given by h upon mv. So, I have put here lambda equal to h upon mv. Now, take this mv on this side. So, it becomes mvr equals to, and here we get n into h and this 2 pi in the denominators, h upon 2 pi. So, suddenly we get this angular momentum is integral multiple of h upon 2 pi by the de Broglie principle. Then de Broglie explained that why electrons which are revolving in the circular orbit and accelerated, not losing their energy. De Broglie said that the matter waves associated with the particles forms standing wave, and we know that this by the property of standing wave that in the standing wave energy can oscillate, but it cannot transfer. So, energy of the electrons is trapped between the nodes, but it cannot escape outside the orbit. So, energy of the electrons remains trapped within the nodes and standing waves are formed. So, by this way stability of the atoms can be defined. Okay. So, 2 pi r equals to n lambda. So, 2 pi r equal to n into h upon mv, and if we take mv here, we get mv r equal to n into h upon 2 pi, and suddenly Bohr, which Bohr himself was not knowing that why atoms are stable, if we take angular momentum as integral multiple of h upon 2 pi, that mystery was unfolded by the de Broglie when he proposed the concept of matter waves. Okay. So, this is very important thing, and this concept belongs to the JEE advanced level thing. Okay. 2 pi r equals to n lambda 2 pi, but I will solve some problem and give you some numerical problem also on the this concept when I will be discussing matter waves separately. So, there are several other things also, and on the basis of Bohr atomic model, finally radius of different orbits we calculated, and different energy levels also. Different energy levels mean different orbits. All these things we will study in the next class, because topic of today's class was Rutherford's atomic model, and in the next class we will study and solve the some good problems on Bohr atomic model. Okay. So, student, this is the end of today's class. In the next class we will discuss Bohr atomic model in detail. Okay. Till then, bye bye.